Okay, am I active? No idea if I'm active. Okay, I think we're live. I assume we're live. Maybe we're live. Whatever. Okay, assuming that anyone's watching this, which is a pretty generous assumption at least. And if you are watching this for some reason, congratulations, you stumbled upon a stream. The recent developments with like a challenge shit are honestly tiring me out. So instead, I decided to do some research, but not just any research, my actual work. So, you, so for people who know me, or probably for people who don't know me, I'm that guy Seele on Twitter, and you would usually see, like, if you visit my profile, it says physicist, translator, home cook. Normally, I'm just the latter two. But for this stream, I am the former, the physicist. And essentially, all I'll be doing here is talk to the void about Bayesian statistics, specifically the math and the concept. I'm supposed to make a presentation out of this by it's 12 midnight, rather it's 1, it's 11 a.m. It's 11:21. My next meeting with my research advisor is in 12 plus 2 hours, 12 plus 3 hours, so 15. Is in 15 hours from now. And I need to get an outline going, which I almost have. So, anyway, Bayesian statistics, the math and the concepts behind it. The book that I'll be basing these slides from is the Statistics, Data Mining, and Machine Learning in Astronomy by these guys. Specifically, Chapter 5, Bayesian Statistical Inference. The Bayesian approach is a numerical realization of common sense. So what do they mean by this? Luckily, I have read up on this topic somehow, some way. But Bayesian statistics is essentially just okay, let's start with a guess. Then we perform an experiment. Once you perform the experiment, you obtain new information. Well, it can be new, uh, it can be new novel information, or it can be old, already known information based on previous experiments or based on the inference used. But then what you do is you update your probabilities, you update your knowledge using that knowledge and then make another inference afterwards. So that's the essence of Bayesian statistical inferences. Let's zoom in a bit. I don't like reading that small text. So blah blah blah. We've already tested main philosophical classical and Bayesian statistical inferences in section 4.1. This chapter will introduce the most important aspects of Bayesian statistical inference and techniques for performing such calculations in practice. We first review the basic steps of Bayesian inference in sections 5.1 to 5.4, and then illustrate them with several examples in 5.6 to 5.7. Numerical techniques for solving complex problems are discussed in 5.8. I will not be discussing those numerical techniques because this is merely the math and the concept behind it. So, cases of Bayesian statistics, motivation versus classical statistics. I guess I should. Posterior probability function. Okay. I will also be checking Discord every now and then. We all need a break. You don't want to all right. Yeah, they're memeing about it now. Why? Okay, I can agree with this, but not on this server, please. Meanwhile, on the other servers, we look for context and we are punished accordingly by trying to derive it from Twitter replies or are masochists. Yeah, don't go on the subreddit too. We're all suffering from that right now. Yeah, it's really petty. Ridiculously petty. My stream's bitrate isn't that good. Fuck off. I need to do research. Okay. So, introduction to the Bayesian method. Highest likelihood. Okay, I'll be discussing this. I'll also be discussing the essence of Bayes' theorem. Actually, I should make a separate section for Bayes' theorem. So, background. Why is it small? I did not want you to be small. Where is that promote tool? So the essence of Bayes' idea is that we apply Bayes' rule to the likelihood function to obtain Bayes' theorem. Okay, all good, all good. We have precise by information. In fact, I'm also describe parameters whose values we want to estimate from data. So essentially, Bayes' theorem states that, okay, if you want to check the likelihood of a model being true given some data D, that is actually equivalent to the likelihood that the data is correct due to model M times the likelihood that the model is in the first place correct, normalized over the likelihood that the data is correct. Well, the probability of data, basically. So D stands for data, M stands for model. Bayes' theorem quantifies the role for combining an initial belief with new data to arrive at an improved belief. It says that improved belief is proportional to the product of initial belief. So this is your PM here. The probability that the initial belief generated the observed data, which is this term over here. So to be more precise, it is something explicitly acknowledged. Well, I will be discussing this, but to what extent? It's also weird to me that they consider this as a controversy. But okay, sure. Sure, why not? Naive by Spog by Visit ka Peter. Sige lang, G. I'm just here doing research. Check ko yung slides ng iba. So, okay, we have the likelihood function. Now, I think I will do the likelihood function a bit later on. It's okay. Frequentists describe probability as randomness. Okay. It just says how likely, but in Bayesian Bayesian frame, probability describes uncertainty. That is okay. It's not how likely a thing is. It's more of how sure are we that it is correct. Plausibility. That is a good. Yeah, I will probably use this. I will definitely use this framing to both describe the history and the motivation. Then we move on to Bayes' theorem. But when would I discuss the likelihood function? Its probability is not frequency according to Bayes. Because if you just do it by frequency, that's just the classical statistics. How long will I be wanting to stream to begin with? So, the beauty of research. Yes, the beauty of research. It's extremely boring. That's why I have Discord on. That way I can look at the fires that piss me off. Amelia Rule 8. Oh God. Oh, fuck off. Yeah, there's so much doom posting. I'm more concerned about Coco than the actual controversy itself. Like the antis going after her. God. Anyway. Back to research. So, Bayesian recipe assess hypothesis. Oh, right. Okay. So, I might, after mentioning Bayes' theorem and the likelihood function, operations and probabilities, just to massage, since this is sort of for undergraduates, I guess. I need to teach undergraduates this. And then you get to Bayes' theorem, which is posterior probability is equal to prior times likelihood. Bayes' theorem or posterior? Well, actually, I could just put it here since hindi pa naman ito yung final video. This isn't even the final video, so posterior. Who pinged me? Ah, okay, yeah. We know, Futsu. Yes, everything's on fire again. Oh. They're all doom posting about the same thing. Why? It's not for statistical. It's Astro Statistics. Posterior. Puta ka. Anyway. It's okay. Posterior probability function. Operations and probabilities. Marginalization. Now I think I could motivate everything in these two. So comment. All right, I'm using my first Google Gmail account. Whatever. Reina already knows that I have like 3 Gmail accounts anyway. Might be sufficient for debating topic. Operations and probabilities, which include the basic probability operations along with also, I'm not a VTuber. I have no avatar. Operations and probabilities. Let's start with definitions, I guess. Hoping me again. Yeah. Oh god, inverse problems. Well, I need to learn this stuff for life. Yeah. Not only that, I need to teach this to our undergrads. Oh, my ass. Anyway. Operations and probabilities. So this should include basic operations and or etc. And actually, I should start with defining over those probabilities. Oh, fuck. Okay. Definitions of arguments. MBI, etc. Theta. Well, I can't type theta, but and or operations slash rules. Basic operations, marginalization, and then definitions of arguments, defining probabilities. And then after this, we get to the juicier parts like hypothesis testing, likelihood functions. statistical tests. I actually have another textbook that I could look from, but I don't think I have it. Deterministic inverse. Yeah, since, well, if you have the data that you could fit, you could essentially, how do I put this? If you have data you can fit, you can essentially backtrace it to the model that you're using via Bayesian approaches. But thing is, you already know what model you're looking at there. Like for these, for what I'm planning to do at least, it's mostly blind. So marginalization, normalization, marginalization, likelihood functions. All right. Before I discuss likelihoods, I need to discuss priors. Well, no, I could actually discuss the likelihood function a bit, but then I'll need to move on to the priors immediately after that. Prior distributions and all of the trappings that are encoded in the priors. Principle of maximum entropy, I know that. Kolmogorov distance, easy. Conjugate priors, much more advanced. I think I'll list all of these down, at least mention them. Then the posterior intervals, just tell me the credibility, marginalization of parameters, Bayes model selection. Okay, these are more advanced now. Hypothesis testing, Occams Razor. Actually, I haven't read past this part yet. So the principle of selecting the simplest model that's in fair agreement with data is known as Occam's Razor. This principle was already known to Ptolemy, who said, "We consider it a good principle to explain the phenomena by the simplest hypothesis possible." So essentially, you're just trying to cut down on parameters. Hidden in the above expression for the odds ratio is its ability to penalize complex models with many free parameters. That is, Occam's Razor is naturally included in the Bayesian model comparison. Well, if you're marginalizing and you find out that a lot of dummy variables don't really make any sense to your model, then you might as well toss those out. Regularization. Okay. Alright, you guys can't see it because I only have one screen. But yes, I only have one screen. So I'm actually looking at the PDFs in one screen and just tabbing to the other parts later on. Like tabbing back to Discord and setting disappointment for myself. Yes. It will turn to fake. Yeah, it always ends in something like that. Wow. No. I hope we lock those channels. Anyway. So back to Occam's Razor. To reveal this explicitly, consider the model M theta and just one of the model parameters, say mu theta 1. For simplicity, let's assume that it's prior PDF. Okay, maybe the likelihood is. Coin flips. Okay, I think I'll be including this anyway. Hoping Mila. What did Shigure Ui say today? Crown yacht. Ha? Anta maji. Shigure Ui ga? Maji ka. Oh well. If she won, she won. Information criteria. So Schwarz criterion related to the Aikake information criterion. I don't know if I'll be including this. I just need, like, I think I'll just discuss up to Occams Razor because that's what's known for most people. And even in astrophysics, most people will do an Occams Razor. So quantifying uncertainties. I'll be mostly following the discussion of the book then. So priors. After priors, we move on to uncertainty quantification. And then maybe this is getting too long. Well, we can always cut down. I actually have to prepare 2 outlines today. One for this and one for what is arguably a shorter paper. I will... let me drag that here. This one. Kusoga. Tebe. いい加減にしてんじゃねえぞ。どこだ？はい、ここ。Search for the stochastic gravitational wave background induced by primordial curvature perturbations in LIGO's second observing run. I actually really like this paper, but I haven't read its references. I'll get to that in a moment. Posterior intervals, marginalization. Okay, model selection. Model selection. So only up until Occams Razor. Non-uniform. Do I discuss non? No, I have to discuss non-uniform priors there. Because most astrophysical stuff is inferred already from other stuff. Yeah, like in this section we address several important cases from where astronomy where prior information greatly affects data interpretation. It's if you know something, then chances are if you're going to receive new information based on that prior information, you're going to be biased to interpret that information based on that prior information. Malmquist bias. So I should probably be a bit more specific here. Flat prior distributions. Non-uniform priors. And okay, finally, the actual thing that I want to discuss. Parameter estimation and model fitting. Now, would I need to discuss all of these? Well, I need to discuss the priors at least. The uncertainty quantifiers, I could probably just hand wave them in a section. Model selection is also probably easy to hand wave simply because it's just a set of principles. It's not like I need to show them the math that much. Yeah, I think we Gucci for this. I just need to work out the math later on. Parameter estimation for binomial distribution. Everyone's going Bayesian this, Bayesian that. And then regression. Yes. Where everything is not a straight line. I should probably take this paper by David Hogg and actually tack it in here. There we go. So if you all haven't noticed, I actually have multiple papers on the ready. Dab. Dabbing in or dabbing out? Decide, Peter. Okay, is Twitter on fire? What moving the goalposts? Which goalposts? Dolchima singing the first Jojo OP. Sono chino sadame. Jojo. So ikoto ka? Oh, a Proto Merlin. Twitter. Yeah. It all sucks, to be honest. I just wish I can do more. Anyway, I think Twitter is not on fire as much. That's good. Or at least I think it's not on fire as much. Back to research. Marginal joint distributions. I don't think I'll need to discuss that in depth. And then model selection. What Angel Milk was discussing. Because they went like, okay, it's more of a deterministic inverse problem. Their size more deterministic inverses. So I don't think they did model selection per se. Simply because they already knew what models they were working with. So regularization. Actually, let me Google that. What is L1 and L2 regularization? L1 regularization. Machine learning methods. Okay. So lasso and ridge. My ass. This might be helpful. I don't know. Well, I'm not going to teach this to our undergrads, but it might be helpful for them to know because we're also doing machine learning on our end as well, actually. Okay. Well, that was helpful. could at least have been more informative. Okay. Hmm. The green and blue functions both incur zero loss on the given data points. A learned model can be induced to prefer the given for the green function, which will generalize better to more points drawn from the underlying unknown distribution by adjusting lambda, the weight of the regularization term. Hmm. So it's essentially minimizing the minimized functions, the minimized space of functions. Interesting. But this is not where my brain is, unfortunately. I will leave the machine learning stuff to our machine learning people. Yeah, I think I'm good with this outline. Let me save this as. Thanks, Google. Let's move this to share with myself. Editor. Send. Thank you for notifying me of my own presentation. Let's move on to what is arguably the easier one, although I'll be leaving this here. Before people ask, yeah, everyone's doing ML nowadays. LIGO, Virgo, even the gravitational wave people are. Basically, if you're doing astronomy, you need to do ML. There's way too much data. Too much data, too little time. And if anyone's thinking, I only use this theme in drafting presentations in Google Docs. I don't like any added flair. Mindoksai. Search for the conveniences of life. Allow me to copy and paste this at will. Fuck. Smaller. There we go. Kapadia. Pande. Suyama. Kandasamy. And Ajis. Shrink this. Then text box at the bottom. Presented by JD Zon. Data computation group. Archive link. Bitch. Okay. New slide. Outline. I've already read this paper, so I already know what to expect. But I need to decide how to structure it. Because the details are, well, okay. Primordial density perturbations generate a stochastic background of gravitational waves through nonlinear mode couplings upon their horizon re-entry. What is that saying is, okay, primordial density perturbations. It's essentially universe, early universe stuff. Nonlinear mode couplings. So these are their main results. They searched for stochastic GW background data on the two LIGO detectors during the second observing run. As far as I know, LIGO Virgo are already in their third observing run. So this is fairly, well, it's not old, it's recent data. And according to this, they do not find any conclusive evidence for stochastic signals in that data and place constraints. So they assume log normal shape. I actually need to know why they assume log normal shape for the power spectrum there. That's their prior. Okay. Okay, I know how to background. So primordial density perturbations, which are just essentially primordial black holes. Then after discussing the background, I go straight into the methods. So Bayesian statistics, basically. Yes, this and this are actually connected. Bayesian inference. This is work. Yes, it works. Shift tab. I learned something new today. So search for the stochastic GW background. The isotropic GW background can be described in terms of the energy fraction omega GW. Okay. This should be build up na. I'll be doing the math probably tomorrow, since I'm not that swamped with homework anyway. Estimate likelihood described in equation 6. Yeah, it's fine, it's fine. Constructing the posterior probability density function. So once we've constructed the posterior from the likelihoods, simulated values, fitting to the data, results, conclusions, extensions. So normally I just end with conclusions, but reading this paper has got me thinking. So okay, a bit of rambling before I end the stream because I want some sleep. See, this work apparently places the constraints on primordial black holes to be around here in this range. So you have CMB, Big Bang nucleosynthesis, etc., etc. GWs are within this range of detectability. What this paper points out is that at the moment there is way too little data per se. No, the signal is way too weak to try and detect primordial black holes, or at least if we're assuming primordial black holes to be the source of those gravitational waves. The signal is too weak to be conclusive of anything. Now, does that mean it's not a possibility? No. It just means that we can't make that conclusion. That a good chunk is due to those primordial density fluctuations. However, what I do want to know is what do future detectors, or rather, what's the limit of future detectors with regards to the capacity to probe these regions there? And so far, we can probe GW, we can probe CMB. But we cannot yet probe around beyond this area. Okay, lensing we can. We can probe lensing, but that's it. There's a huge gap going from lensing to cosmic rays and going back beyond that to the gravitational, to the galactic gamma ray background. So yeah, I'm pretty invested in this, if only to develop more techniques for detection. Uh, I'm tired. Are we still on fire? I don't think so. Oh. My dog is snoring. That's good. At least he's alive. But anyway, I guess I've done enough for this morning. Rather, okay. Brown bag present. Brown bag number 2. So I'm okay with these outlines. We'll be fleshing these out later today anyway, assuming we have a meeting later today. Since I don't even know if it's like 1 a.m. Yeah, it's around 1 a.m. at the moment. Not too bad, not too good. I realize that talking to the void like this is actually pretty helpful for me, for some reason. Oh, Bayesian Statistics invitation to edit from myself. Nice. Eh, the fires are gonna keep on raging. Yasumitai. De wa, oyasumi shimasu. Goodbye and good night.